Where's your coffee?
I only want to study.
Okay, you could take a nap during it. Nothing.
Steven told me.
Who's your teacher?
Hold on.
Oh, no, don't. Okay. Right. Okay. Let's continue that. Oops. Okay. Next now. Equilibrium of coplanar forces. Oops. There we go. Oh, sorry. Didn't know we were still on that. Okay, equilibrium of coplanar forces. Again, not a big lesson in terms of new material, but again, just like the last lesson, sometimes students find it a bit confusing. Yeah?
Is it the right word, like EQUA?
Equilibrium
Is it I?
is what I. No, tell me, because sometimes I spell things wrong. What is it? EQ.
UA.
Yeah.
Ah, I know why you're thinking that, like equal.
Yeah.
No, this is right, yeah. Okay, you got that? Yep. Yeah. Okay. Okay. Come on. There you go. Okay. This is a. Well, actually, let me just draw it first with my pen. Here's an example of a special type of system. Well, that's the ground, by the way. So I'll draw a ladder here. Like a ladder. And just to be clear, this wall is smooth and this ground is rough. So you have a force here that stops the ladder from sliding. This is a friction force. Yeah? And also, sorry, I drew it the wrong way.
Yeah.
You're totally messed up. So you have a friction force here and a reaction force here. So just like the hinge, it means in total there's like a force, something like this, for example. Yeah? There's also a force out here from the wall, and the reason it's not at an angle is because in my picture here the wall is smooth. So that means like this, there is no real force up when the ladder is against it. The force is only coming from the ground. So you can see there's a friction force on the carpet because I don't slide forward. There's a friction force stopping me, but there isn't one on the wall in my picture. Now I know in real life there is, but just in my one to make it simple, it's not. And there's one more force here, the weight of the ladder. So the three forces are: there's a weight here, there's a weight here, there's a reaction here, and there's a reaction out here. And this one is at an angle, whereas this one is horizontal. Okay. But of course there's another system. Remember last lesson we just did the cantilever. So we have three forces here. There's a weight. Yeah. What else did we have if we put a stay here? We have a tension, don't we? And what else? A reaction then. In other words, the point I'm trying to make is it's actually quite a common and special system in physics to have three forces in the system. It's actually a special type of problem in physics. Here's the example with the ladder. So you have the weight, the force from the ground, and the reaction. And it's a special type of problem in physics. It's special because there's three forces on it, and it's in equilibrium. It's balanced. So this is what we're looking at today. We're looking at these special systems. And something very interesting happens when we have three forces. When there's three forces in the picture, if you draw their lines of action, line of action, line of action, line of action, you'll discover that they all meet at the same point. Line of action, line of action, line of action. They all meet at the same point. Let's try and prove this, okay? So here's the theorem. So let's say we have some object and it's not moving, it's in equilibrium, and there's three forces on it. So we'll say there's one force here, we'll call this F. We'll say there's one force here, we'll call that G, and then we'll say there's one force here, we'll call that H, and it's balanced. And I want to prove that they all meet at the same point. Okay, well, let's just look at F and G. We all agree that F and G, unless they're parallel, I should say none of these forces are parallel, because that's silly then. Unless they're parallel, they'll meet, because they're two lines. Yeah? Where they meet, I'll take this as the turning point. Because remember last time I showed you it doesn't matter where you put the turning point, you still get the same answer. So I'll make this as the turning point. Okay, so this force, is it clockwise or anti-clockwise if I use this as the turning point? This F, we'll call it D1 and D2. So, clockwise or anti-clockwise?
Anti-clockwise.
No. No.
None.
Why? Pass through the turning point. So this one has 0 to offer. What about the G? 0 to offer. So the total turning force only comes from the H. But there shouldn't be any turning force because it's in equilibrium. Right? So you're forced to say that the H must pass through the centre as well. So this is the three-force theorem. The three-force theorem says that when three forces act in the same plane on a mass in equilibrium, then all the lines of action meet at one common point. They all must meet at one point. This is the three-force theorem. Please note this. Plane just means like a flat surface, like it's all just x, y, no z. Okay, did you note that?
No.
Has anybody seen that theorem before? Or is that something new? I don't know. You haven't seen that before? Huh? Have you seen this before in high school? You have, yeah? Yeah. Middle school. Smart middle school. Okay, can I continue? Yeah? You understand the idea here? Yeah. Now, if I had two forces that were balanced, one force is this way, if they're balanced, what must the other force be? It has to be like this, so that when you add them together, you're back at zero. Same idea if you have three forces. If I have three forces, 1, 2, 3, and they're balanced, if I add them together, they almost go back to zero. They almost cancel. Okay? I'm going to just draw these forces like this. There is another way to state the theorem that I did previously, and we can't really do it just yet. KJ, leave poor Jerry alone. He's so sick. You should be supporting him.
No, I mean just one.
No, you don't. You haven't been Irish sick yet. Irish sick is much more difficult than Korean or Chinese sick. It's all up here. Right, Jerry?
I'm also
No, not necessary.
I know I'm in muscle.
No. When KJ is sick, we'll remember. You should be asking Jerry, would you like me to make you some Korean chicken soup?
Yeah.
You know? Yeah. Support him. Okay. So as I was saying, Jerry, I'll give you my little tip for when I'm sick like you. You need to eat very spicy food.
Ooh.
Yeah.
Yeah, come out.
Is it true?
Yeah. You need to eat very, very spicy food, like Indian food.
No, it's not spicy.
Yeah, it's true.
Korean is the best.
You have spicier food.
Chinese,
No, I don't know. It's like
Don't eat spicy noodles.
no. Anyway.
Korean spicy
I
noodles.
kind of guess.
Yeah, you make him some spicy noodles. Be his friend. Okay. So as I was saying, if we have three forces, there is another version of the three-force theorem, which I can't really prove because it needs something from maths class that we haven't done yet. So I'll just give you the result without the proof. Again, if you have the three forces that are balanced, we'll call this one F1, we'll call this one here F2, and we'll call this one here F3. And we'll say that this angle here is, I'll call this angle A, and then this one here, which is opposite to B, and this one here, C. Another way to state it is that F1 over sine A equals F2 over sine B, which could also equal F3 over sine C. Now some of you might be thinking, that kind of looks familiar to something I did in high school maths. What does it look like? Yeah, what's this called? Yeah, which we haven't done in maths yet. So another way to state this theorem's result is by this formula, which is also useful. So can you add this to your result, this and the picture? Sine rule, correct, yeah.
Is it proving the force of adding the vectors? three vectors.
Yeah, it's to do with adding three vectors making a triangle, and the relationship between the forces is like the sine rule. Continue? Not yet? Continue? Yeah? Okay. Right. I did the proof. Okay, let's see. A 10 kilogram ball of radius 5 centimeters hangs on a wall by means of an 8 centimeter string. So I'll draw this for you. So you have the wall here. You have the ball here. This is, what did I say? 5 centimeters, yeah. And the force here is a 10G. And it hangs by a string on the wall like this. And this is 8 centimeters. And my question is, what is the tension in the string here? Okay, I am missing one force on my diagram. What am I missing? The reaction. And which way will this point? It's perpendicular here because I think I said it's a smooth wall. Yeah. Now, using the three-force theorem, I know that these three must all meet at the same point, which means this tension force is pointing to the center of the ball. So let me just draw that triangle. How big is the base? 5. And how big is this side? 8 plus 5, which is 13. So Pythagoras tells us this is 12. And our calculator tells us the angle is not 45 here.
67.38. 67.
Oh, sorry. Okay. Now let's look at the T. The T has two components, doesn't it? So let me just zoom in here. Dun, dun, dun. So if I draw it this way and this way, this is T cos and this is T sine. But actually no. Yes. This angle here is 67, so this angle here is 67. So this is the T cos and this is the T sine of 67. It's this one I care about, because what I can say now is T sine 67.38. What must that equal? 10G. The up equals the down. So I have my answer now, 10G over sine 67.38. That's that. Minus? Okay. 0.28. Much easier than using turning force. But we can only use this because there were three forces on it. I'll do another one. Write this one down, please.
Why don't we use this method for the last topic?
That's what I'm just about to do. So I'm going to take one of the questions we did and have a look at it now. Yeah. Oh yeah, that looks the business. Thanks. You're welcome. I got something from someone. But no, but you see, you coughed over it and you touched it. Huh? Must I have this now?
Yeah, we're just.
You don't need this?
Not anymore, now that I have this. In fact, I don't need you anymore.
Okay, thank you.
Good news. What's that you have? Korean? Are there places in Ireland you can get Korean food, like a supermarket, or not? There are?
But I found one place. They have Korean barbecue. That's good.
Korean barbecue?
Yeah.
Not bad. Not bad.
It's like all you can eat Korean barbecue. And then all you can eat sushi.
All you can eat sushi? What is that? No, it's just sushi is so small. You can keep eating it.
It's for the IST. It's over there.
Oh, over there. Oh, right, okay.
Like 40 minutes from here.
Oh, 40 minutes.
You have to cross the easy.
Yes,
Easy.
Liffey, yeah.
Easy.
Yeah.
First, and
Oh.
you can buy it.
Okay, so it's kind of far then. Right, have you written this down? Yeah. Not yet, okay.
When we are in exam, then it's 2 hours and half, 2.5 hours.
Yeah.
Is it enough time to solve all of questions?
Yeah. In my experience, the time for the physics exam is okay. The maths sometimes can be a little bit tight, because sometimes the questions can be long. But the thing about the physics exam is the questions are quick if you know how to do them. For example, this question, because I knew how to do it, I can do this quite quickly. That's the key for the physics exam. It's once you know how to do them, you can actually do them quite quick. So the good students have extra time because they know how to do the questions, so they just do the question. The weaker students will sit there thinking, going, you know. Yeah.
I think it's difficult than that.
What's that? The physics?
Yeah.
The English, huh?
Yeah.
Yeah. Okay. I want to do another example. I want to look at that sine example we did in the last lesson. So let me just redraw it. It was 40 by 20. So here, what was the weight of it? 2 G.
Yes.
And there's a tension here. Oh goodness. Oh, not pretty. I'll fix that. Hang on. There you go. Okay, and what did I tell you? What else did I tell you about the length?
40.
This one? That's everything I told you?
And 20 cm down. The side.
But we don't actually need to know the
Yeah.
Yeah, but
length. Yeah. And there's a reaction force here. So do you remember throughout the whole question, I first had to find T. Then once I found T, I could find Rx and Ry. Then once I had Rx and Ry, I could find this angle. And what was this angle actually? Was it 45 or something?
Yeah,
Yeah.
45.
Okay. So, let's use the three-force theorem. Because there are three forces, their lines of action must meet. So here, and here, they all must meet here. So I know this side is 20 and this side here is 20. What else can I know here in my picture? Let's see. Well, I know this whole length here is 40 root 2, don't I? Yeah. Now, because this is in the middle, it actually breaks this up into two equal parts. So this would be 20 root 2 and this would be 20 root 2. Because this is in the middle here, it also makes this in the middle. Now I don't know if you knew that, but I'll draw it here. If you have a line and a line like this, and here's like A, and then let's say here is B, and I put something in the middle here and draw it straight up, that's also in the middle of the other line here. Okay? Right, so that means I know each of these. Now if you look at this picture, I know this is 20. I know this is 20 root 2. So using Pythagoras I can get this. Let's just say it's square root for 800 minus 400. So 20 root 2. So this side here is 20 root 2. Oh sorry, 20, thank you. This side here is 20. Now if this is 20 and this is 20, then this angle here is tan inverse 20 over 20, which is 45 degrees. So we could get to the answer much quicker. But that's actually convenient, because now what I could say is or cos 45 must equal t, and we know that this one is 45. I can also say r over root 2 plus t over root 2, that should equal 2g. That this one plus this one equals this one here. Now look at what we have. How many equations? 2. Yeah, so that means r and t are equal. So that means this will be, for example, 2r over root 2 equals 2g. This is right, r equals root 2g. If I root 2?
Just 2 divided root 2.
You're confusing me. If I put this in here, I can say r over root 2 plus r over root 2, which is 2r over root 2, which equals 2g. The 2's cancel, so r is root 2g. Well look, it's simple. What's root 2g? And we'll check if it's the same answer. And what did I get last time I did it? So, by using the three-force theorem, we can actually do the question backwards, and it's actually quicker. Because now that I know the or, I can also know the t. Yeah? So, this was much quicker than the other way I did it. But there's a complication. If I added in an extra force, like if I put a weight at the end here, then I can't do it this way anymore. Why not? No, that's not the problem actually. No. 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 No.
The forces are more than 3.
Yeah, there's 4 forces. Okay. More number of forces. Okay.
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 Right. So are we happy with this new useful theorem, the three-force theorem then? And you're right, Lee, you can actually use it for the previous lesson too, to help you do the questions. Yeah. Let's see, do I have a... no, I don't have another example here. So I think now... see, I'll give you the... Yeah, for a few minutes now, I'll give you some of the questions here. Well, actually, I just want to do one quick one using the signs. So, for example, let's say, like an exam question might be, you have something hanging from the ceiling. So you have a string here, a mass here, and typically in the exam they might give you these angles. So this could be like 30 degrees. This one here, I don't know, could be like 40 degrees, and you're given the mass here. We'll say this is just 1 kg. Okay, so how many forces are there here? 3, and they all meet where? At the 1 kg. So we'll call this one T, this one S, and this one here 1G. And the question is, find T and S. And if we use our theorem, we can do this quite easily. So first we have to find this angle. This angle here is 110, is it? Now, how much is this angle here? That's 30. And this angle here? That's 40. Yeah? Now, if I go dot, 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 don't confuse me, dot, 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 that's 30. This one here? That's 30, because that's the same as this one. And this one here? That's the same as something. Hang on, well let me do the other side. Oh yeah, of course, that's 90, so that's 60, thank you. Now this one here is the same as this one, which is 40, so this one's 50. Great, so in total, this angle here, 50, 60, 70, 80, 90, 120 degrees for all of this. And this one here is 110, so that is 230. So does that make this one 110 as well?
130.
Huh? 130, great. So this angle here is 130. So we can say T over sine 130 equals S over sine 120 equals 1G over sine 110. If I take these two, I can say S equals sine 120 sine 110 times 9.81. Can someone tell me that, please?
$9.04.
9.04 newtons. Now, if I take this one with this one, I can say T over sine 30 equals 9.04 over sine 120. So now I have the T. T is sine 30 over sine 120 times 9.04. So now I have the T. Huh? Well, 130, thank you. 130. Yeah? What's the T?
8.
Yeah? Just say is that?
7.9.
997.
Yeah, okay. Got that? So, you don't have to use this theorem here to do this one. You could use turn-in forces again. Where would you put the turn-in point to make this a little bit easier to do?
Middle of the ball.
No, that makes it too easy because all the forces go through the middle of the ball, so you get 0 equals 0. So we can't use the middle of the ball. Yeah, I think somewhere maybe on the ceiling. So if you put it here, and if you look at this as the turning point, the T is gone. So you would have, if I call this distance D1, you would have D1, but the problem is it's not S. You have to look at because this angle here is 110. Yeah, it has to be perpendicular. It's 110, and you just need this component. It's almost like you have to take that and resolve it. So it's 110, this one here is 90, this one here is 20, so this is S cos 20. So it'd be D1 S cos 20 equals, and then it would be this one. So now you need to know this distance. You know? And the big problem here is I didn't give you any distances, which is a problem. So you realize, oh, this theorem is quite useful because if I didn't have this theorem, then this problem becomes much more difficult to do. So it's actually a very simple but a very useful theorem. What I find very interesting is in the exam, he never uses this theorem to answer questions, even when you can use the theorem. For example, yeah, I know, the exam writer. For example, if you had this question in the exam, which way do you think he does it? Well, you might think, oh, he'll use the theorem I did today because that's easier. Instead, he'll do it the way we did it in the last class. This is good news for you because it means he's making the question harder for him, so he's giving the question more marks, but you can do it the easier way and get the full marks. Do you understand what I'm saying? So you have two ways to do this one. He is marking it as if you're doing it the harder way, but he doesn't say to do it that way, so you can do it this way. So you can get full marks by doing it a much easier way. So my tip for the exam is always check if there's 3 forces, because if there are 3 forces, then it's probably easier to use the theorem. Again, I've seen this question in the exam, and you can see how easy it is by using this formula. And do you think he uses this formula? No. I don't know why this is. I don't know why, but it's good news for you. It's good news. I think a couple of years ago, maybe 2 years ago, the exam question was like this. You had a door on the ground, and the you know, like a trap door on the ground, the door opens up and you fall down. It wasn't balanced though. The center of gravity was like here. You know, maybe this was 20 and this was 10 centimeters. There was a reaction here, and there was a tension here. And this question had lots of marks because the way he taught you would do it is the previous lesson. But in fact, if you use the theorem, you get this here. So this is one of these questions where it was easier for you to do one part C, one part B, one part A, to actually do the question backwards. to find the angle first, not last, and work backwards. Yeah. Sometimes in the exam you will notice that strangely you might find it easier to do it backwards.
In the past as well, we've done backwards. Like maybe the information in B we used to get A.
Exactly. Maybe something that you have to find in B will make A easier to do. Yeah. So it's important to read the question fully before you start, because surprisingly it might be easier to start at the end. That doesn't happen often, but I'd say maybe 2% of the questions are like this. But when it does happen, it's a real bonus for you because you found an easier way to do it to get the full marks. Okay? Now, let's see. I'll give you the questions. Unfortunately, I'm sorry, I didn't have time to make the answers for today's lesson, so I'll have to make that today. I'll send you a text when I have the answers.
You just want to try out the system.
In fact, I might even send you the answers in the text. No, I'll give you a clean one. There's probably have chocolate all over that one. There you go. What class have you got now? Oh, it's
Where you have to go.
where it is.